Doing the Calc BC 2018 free response. This is question 1 on the calculator section. So this problem is effectively just a flow in, flow out problem. Only they use a model of an elevator, or I'm sorry, escalator. But the basic idea is you have things entering into some kind of system, and then you have things exiting. And the rate that they enter in is R of t, and the exiting rate is L of t. L of t is not explicitly defined here as L of t, but it's just this constant rate of 0.7 people per second. And R of t is this nasty equation up top. So let's go through and kind of try to knock this out. So let's look at part A. How many people enter the line for the escalator during the time interval t from 0 to 300? So it's purely concerned with entering. So we want to use just the R of t entering function. Now the units of R of t are what? It's people per second. So intuitively, if I just want the number of people after some time, I can do R of t times some delta time. This tells me the number of people over some time interval delta t. And in the calculus sense, that's pretty much the same thing, but R of t times d of t, where t varies from a time 1 to a time 2. So these questions, the calculation itself isn't as important. It's more just setting up the problem. You can get a fair number of points. At the end of the day, calculator is there for a reason. Trying to hand solve this R of t for the first piece of the piecewise is pretty nasty, and there's really no sense in doing it. That's why they give you a calculator. So just quickly, let's solve this. The number of people in the scenario are t1 is 0, our end time is 300. We have R of t. I'm not going to write it out because, again, this is calculator. And dt, where dt varies from 0 to 300. We solve this out, and what we get is it's equal to 270 people who enter the elevator. I'm sorry, I keep saying elevator. Escalator. My pen's going all crazy. Escalator from times. This epsilon just means in, so times in 0 to 300 seconds. Cool. All right, part B. During the time interval 0 to 300, there are always people in line for the escalator. How many are in line at time equals 300? So it's kind of the continuation of part A. So again, calculation, not that important, but the model is very important. So we want to know at 300, what are the net number of people on the elevator? Not who entered, not who left, just the net number of people. So the net number of people, and I'll call this function n of t, is the number of people entering, which is R of t, minus the number of people leaving, which is L of t. R of t we know. I'll leave it as just R of t. And L of t is given as 0.7. Both of these are, and that's equal to n of t. And again, the unit for these is people, which I'll abbreviate as ppl, per second. So first let's find how many people are on the escalator from 0 to 300. So very similar to part A, we want to integrate our net function over the time interval 0 to 300, which is really equal to r of t minus L of t dt over the same time span. And since integration has a property called linearity, you are allowed to make this statement that this equals r of t dt minus L of t dt from 0 to 300, 0 to 300. So we just solved in part A this exact integral. And we found that it was equal to 270. So 270 people have entered the escalator between the times 0 to 300. If L of t were 0, what would that mean? It means no one leaves. So they enter and they stay on there. So there'd be 270 net people on it. However, L of t is not 0. It's 0.7 t, I'm sorry, 0.7. The integral of that is 0.7 t from 0 to 300, which equals 210. So now we have, let me go over here, we have 270 minus 210, which equals 60. So again, just the intuitive explanation to this. Over the time period 0 to 300, over the 5-minute interval, 270 people entered, and then 210 people left. So overall, there were 60. Now, one little caveat or point to be careful at is in the problem it states that you start off with 20 people. So really, it's 60 plus 20, which is 80 people. 80 people who are, there's PPL, on escalator at t equals 300. All right. And then let's move on to part C. For times greater than 300, what is the first time that there are no people in line for the escalator? So at times greater than 300, what do we know? We know r of t equals 0. That's defined in the problem. It's a piecewise function. But L of t is actually the same. L of t just remains constant, equal to 0.7. So we want to know after 300, what's the net number of people at what time is the number of people on the escalator equal to 0? So we know that at time equals 300, from part B, we have 80 people currently on the escalator. So we have 80, if you look at it as a function, we have 80 people that we start off with, and every second we lose 0.7. So we want to know really what this point is. As a function, you can model it as 80 minus 0.7 times t equals 0. Just keep in mind, L of t is a rate of change, so the slope in this scenario is 0.7. And solving that is not very difficult. 80 equals 0.7 t equals 80 over 0.7, which equals, let me calculate that right now, 80 divided by 0.7, which equals 114.28 seconds. So 114.28 seconds after t equals 300, we have 0 people. So the time from the start is going to be, I'll call it t0 to indicate the times when we have 0 people. Actually, that's kind of misleading. I'll say t final. T final solution is the 300 plus 114.28. Okay. And then the very last part, and this is 4:14.28 seconds. And then the last part of the question is for t in the range of 0 to 300, at what time t is the number of people in line a minimum? And then define your total number, find people in line at this time. Okay. So I'm kind of running out of space, but let me go over here. So part D. So now we're back in the 0 to 300 range. So we can't get lucky and just kind of ignore R of t because R of t is not 0 in this range. So again, let's go back to our net equation. N of t we saw before was equal to R of t minus L of t. And whenever you see minimum or maximum, it's probably a derivative. So N of t isn't the number of people, it's the rate of people on escalator. So the number of people, which is, I guess I shouldn't have used N of t, but it's too late at this point, is the integral of N of t from 0 to t for some specified t. This would give us the number of people on escalator. And this is equal to, we'll just leave it at this. Then we want to find the time when number of people is a minimum. So basically, if this were a function, let's just call it, not to be confusing, let's just call it z of t. To find the minimum or max, it's pretty straightforward. We just want the derivative of z of t, d over dt. Now in this case, it's kind of interesting. So we want the derivative of this, N of t, dt, which is equal to what? Well, it's equal to the integral, well, the derivative of the integral of R of t minus L of t dt. And then we want to know when this function is equivalent to 0. And really what that's saying is, not to be pedantic, but just for sake of clarity, we're taking d over dt of really just the integral of R of t dt minus d over dt of the integral of L of t dt to equal 0. And derivative of integral is just a function. So we have R of t minus L of t equals 0. R of t, we know what it is. I'm not going to write it out. L of t is 0.7, so we want to find really this. When does R of t equal 0.7? Again, this is calculator that you're not expected to be able to hand solve this. It's a pretty ridiculous, nasty function. And when you graph it out, or however you solve it on your calculator, you find two different times. T1 being equivalent to 33.013 seconds. And then a second value where it hits where it hits 0.7 of 166.575 seconds. So at these two times, the function z of t, which is the number of people on the escalator, is at a min or a max. We don't know if it's min or max yet because we haven't actually plugged it in, but let's just test now to see is it at min or max. So the time, and let's say the number of people. So at 0, we know there's 20 people. At T1, which I don't want to write out, but it's just this 33.013 seconds. T1, to find, we have to actually plug in this time into, where is it? this equation. I know it's annoying, but there's really no other way to solve it. So you plug this in, and I just want to be extra clear. It's the same thing as doing 0 to, instead of 300, 33.013 of n of t dt, and you can solve that. The value you get is, to the nearest whole number is approximately 4 people. And t2, same method of solving it. You have to do 0 to t2 of r of t minus l of t dt. And what we get for that one, rounded to the nearest whole number, is approximately 158 people. We know that at 300 seconds, which we found, I think, in part B, they were 80 people. Okay, so switch screens real quick because I did an initial explanation that I wasn't crazy about. So let's just, before we finish, kind of look at these last 4 points. So keep in mind that T1 and T2, which is right here, the T is 33 seconds and 166.575. These are our critical points. And then T equals 0, right here, and T equals 300, are just the endpoints where the R of T stays and is defined by this one function. Clearly, here, T1 represents the min. And to further reinforce that, we can do a kind of a derivative table. If you draw a number line and mark point T1 time T2, and the sign and the value we're going to put above it is going to represent the derivative. So what we just found was a T1 and T2, and just to be more clear, of n of t. At T1 and T2, that's the point where there is no rate of change. At values less than T1, you can plug in anything under T1. If you plug in 0, you'll see that you have R of 0 minus L of 0. R of 0 is 0. L of 0 is 0.7, which is negative. So here, all the derivatives are actually negative. If you plug in a value between 33 and 166, you'll find that it's positive. And then anything greater than T2, the 166, is going to be negative. And intuitively what that means is the rate of change is decreasing. You have a negative slope, kind of bottoms out to 0 at exactly T1 before increasing, increase, get to a certain point, which is T2, and then it goes back to decreasing. So T1 here represents the min, and that's reinforced by what we saw in this table, where 4 is by far the smallest value, but I think it does help just to have a more complete answer to also include, a table like this to show you understanding that kind of conclusively proves that T1 actually is a min. It would be a bit of an edge case, but there could be a scenario where these are both actually going to be min, or this isn't necessarily a min, it could be a max. Just for completeness, this is a good way to really reinforce your solution. And that concludes the first problem of the 2018 Calc BC free response section.